800 feet below the streets of Manhattan, in the middle of the 1930s, men were drilling through some of the hardest basement rock in the world by the light of bare bulbs strung on cable. The geology at that depth had been sampled at intervals before construction started, core pulled from boreholes and logged by engineers who noted the rock type, the degree of fracturing, the water content at each sample point. Those samples told a precise story about the rock where the bit had gone. They said nothing reliable about what the rock was doing between those points, where the faults ran, where ancient diabase intrusions cut through the schist at angles no surface measurement could reveal, where pockets of pressurized groundwater sat behind walls of stone that had never been disturbed. Nobody knew until the drill found out the hard way. New York City's first water tunnel had come online in 1917, running from Hillview Reservoir in Yonkers, south through the Bronx and into Manhattan, buried several hundred feet below the street. The engineering was sound, and the water flowed, but a single buried conduit serving millions of people was, by the 1920s, a risk city planners understood they could not hold indefinitely. If the lining cracked in a critical section, if a fault shifted under sustained hydraulic load, the water supply to the boroughs that tunnel served failed entirely. There was no bypass line, no way to isolate a damaged section and keep the rest of the system running. A second tunnel had to be built on a parallel route, deep enough to generate the hydraulic pressure to reach the upper floors of the taller buildings that had risen since the first tunnel was designed. That pressure requirement pushed the deepest sections of the route to 800 feet below the street. The men who would dig it were called sandhogs. If you're enjoying this story so far, don't forget to hit the like button and subscribe. Drop a comment telling me where in the world you're watching from. I love hearing from you. That name had come from an earlier generation who bored under the Hudson and East Rivers through soft river mud, working in pressurized chambers kept dry by compressed air pumped from the surface. The air pressure pushed back against the water table and held the soft ground from caving into the face. Coming back up through the pressure locks too quickly caused decompression sickness, joint pain, paralysis, and death. The sandhogs working the second water tunnel were not doing soft ground work. They were going into Manhattan schist and gneiss, dense metamorphic stone that had been compressed and recrystallized over hundreds of millions of years. The name carried forward even though the geology had changed entirely. The labor force that came to the second tunnel was not a single group. Many experienced drill bosses and crew leaders were Irish, or the sons of Irish men who had followed the tunnel trade through decades of New York construction, from the early subway drives and utility tunnels through the first water system. West Indian workers were a steady presence in the labor force throughout the project. African American workers who had migrated north in the preceding decades worked alongside the drillers as laborers and learned the drill trade from inside the heading, watching and eventually moving into drill positions as experience accumulated. Men who had worked the Pennsylvania anthracite mines arrived with a different kind of rock knowledge, one shaped by coal measure geology but directly applicable to the mechanics of drilling and blasting in fractured and variable ground. The knowledge connecting all of these men to the work was not formalized. It passed through families and crews, from experienced drillers to the younger men beside them. How to angle a cut hole for the foliation planes in the current face, what the pitch of the running drill told you about the rock ahead, how to read the cuttings for early warning of a change in rock type. Those things could not come from any manual. They came from standing beside men who already knew, getting those men and their equipment to a working face 800 feet below street level required sinking shafts first. Shaft crews worked ahead of the main drive on each section of the route, dropping a vertical opening through the rock by the same drill and blast cycle that would be used in the horizontal headings. The geometry made shaft work slower than heading work in a way no amount of added labor could overcome. In a heading, blasted rock went into rail cars on narrow gauge track and was pushed to the shaft bottom for hoisting. In a shaft, every piece of blasted rock went straight up in a bucket on a hoist cable, one load at a time, the hoist cycle lengthening with every foot the shaft deepened. At 800 feet, a loaded bucket trip took several minutes end to end. The crew at the bottom could not drill the next round until the muck from the current one was out of the hole. A shaft gang working at depth might finish a 10-hour shift, having advanced 3 feet, in rock that broke into large irregular pieces, requiring sledge work before they would clear the bucket rim. 3 feet was not guaranteed. Air inside a shaft was harder to manage than in a heading. A heading open at both ends had some natural through-draft. A shaft was a vertical well with one opening at the top, and the combustion products of a blast had nowhere to go but straight up through the same column of air the crew used to descend. Compressed air piped down helped move the gas upward after each round, but at depth, the exchange was slow. Crews waited above ground after every blast, carrying no instruments to measure what was in the shaft below them. The test for safe re-entry was a carbide flame held at face level at the shaft bottom. If it burned steady, men climbed back into the cage. Down at the heading face, before the first drill was positioned, the drill boss walked the rock. Every face in Manhattan schist shows foliation, the parallel banding that records the direction and angle of the original metamorphic compression. Those planes were the rock's natural lines of weakness. A hole drilled parallel to a major foliation plane gave blast energy a path along the plane rather than into the surrounding rock, and the round moved less material for the powder it consumed. A hole drilled to cut across the foliation at the right angle could use those planes as natural brake lines and pull a larger section free with the same charge. The boss marked the face before the drill crew set up. A drill boss who read the current face correctly could move a heading faster and cheaper than one who ran a standard pattern, regardless of what the rock was showing. A full drill round for a heading of the second tunnel's diameter used between 30 and 40 holes, each bored to 6 feet, with pneumatic jackleg drills fed by compressed air through rubber hose from compressors at the shaft bottom. The jackleg was a percussive drill mounted on a hinged steel leg that the driller positioned and braced against the floor or wall, adjusting the angle by hand before opening the air. The machine struck the bit at several hundred blows per minute, rotating it between strikes to clear the cuttings. Penetration in clean, massive schist ran about a foot per minute. In broken ground near a diabase dike or fault zone where the rock changed hardness within a single hole, the rate dropped and the bits wore faster. A blacksmith worked near the shaft bottom, sharpening bits on a powered grinder and sending them back to the face through a runner who moved continuously between the shaft and the heading. The cut holes were loaded and fired first. Angled inward toward each other near the center of the face, they broke out a central void that gave the surrounding charges room to throw broken material into. Without that void, blasting the lifters or the perimeter first would compress the rock rather than free it, and the round would freeze, stone cracking in place instead of throwing loose. The lifters at the bottom of the face fired after the cut, establishing floor grade. The back holes came next. The perimeter holes, angled slightly outward, shaped the final tunnel wall. Dynamite went into each hole packed on wooden rods and tamped with clay, each hole fitted with a detonator on a leg wire. The firing sequence staggered each group in milliseconds, every blast using the void space opened by the one before it. Every man cleared the heading before the round fired. If you're hooked on this story, make sure to subscribe and turn on notifications so you never miss an upload. Your support means everything and helps me bring you more emotional stories like this one. After blasting and after ventilation cleared the gas, shovelers moved into the heading and loaded broken rock into rail cars by hand. Large, irregular pieces that had not fragmented finely enough were broken with hand sledges. The cars ran on narrow-gauge track that the track crew extended with every round advance, pushed by hand to the shaft bottom and hoisted to the surface. Alongside the track, the ventilation duct ran the full length of the heading to the face, drawing fresh air from the shaft and keeping gas levels low enough to work. The electrical supply cable ran beside it. As the face moved, the track extended, the duct extended, the cable extended. All of it advanced with every round, 12 to 15 feet at a time. A crew, moving 3 rounds per shift, relocated the entire working apparatus before the shift ended. When a drill hole pushed water back instead of cuttings, work stopped at that hole. The powderman assessed the inflow. Light seepage could sometimes be worked around. a charge loaded deep in the hole with gelatin dynamite that resisted water damage better than straight formulation, fired before enough water accumulated to affect the detonation. Heavy inflow stopped the heading entirely. Cement grout had to be mixed on site and pumped under pressure through pipes driven into the rock ahead of the face, filling the fractures and voids carrying the water. The grout needed time to set in cold, deep rock, a day at minimum, often longer, depending on the temperature at that depth, and the volume of void space that needed to be filled before the face was sealed. All the pump equipment had to come down the shaft and into the heading before the first stroke. Heading advance stopped and waited. When work resumed after grouting and the next round came off, the face behind the blast was often different rock, the dike or fault that had been carrying the flow, now behind the heading where it no longer mattered. Rock falls were a hazard separate from groundwater and came without the preliminary warning sign that water gave. After each blast, before mucking started, the scaling crew worked the back and the walls with long steel bars, knocking loose material down before it chose its own moment to fall. A blast that cracked a section of rock without fully dislodging it left pieces hanging above the working space, held by friction and the random interlocking geometry of broken surfaces. Scalers brought most of it down deliberately. What the bars could not reach because the heading was too tall or the fractured zone was positioned where the bar had no useful purchase, was carried on timber sets, frames driven against the back and wedged tight to support the loose material until the concrete lining replaced them. In badly broken ground, sets went in before mucking was finished because the crew could not work under an unsupported back while clearing the blast pile. Falls from the back killed men in hard rock tunnel work throughout this period, most commonly in the scaling and mucking phases immediately after a blast, when the ground above the heading was freshest and most disturbed. The sandhogs moved through the hazard by moving fast, getting support in place and muck out before the zone above had more time to work loose. Keeping a heading on its design line through all of this was the surveyor's task, and the survey had no physical anchor underground except what had been carried down the shaft. The tunnel centerline had been established at the surface with optical transits tied to the city's permanent geodetic control. Transferring that line underground required plumb wires, fine steel wires hung from precisely located points at the shaft top, with weights at the bottom to hold them vertical. At the shaft bottom, a transit operator set up the instrument and shot a bearing from 2 plumb wires into the heading, marking the centerline on the tunnel wall at 2 reference points. As the heading advanced, the surveyor extended those marks setup by setup, each new mark derived from the previous 2, the chain reaching back through the full length of the heading to the wires at the shaft. Vibration from nearby blasting could disturb a plumb wire mid-hang. Dust on the transit lens changed the clarity of the sight picture. A wall mark bumped out of position by a passing railcar might not show the shift until the next survey setup found the discrepancy. Angular error was the invisible hazard in the survey chain, a pointing error at the shaft top that was too small to catch in the surface measurement propagated forward at the same angular rate with every underground setup, generating a position error that grew with every 100 feet of advance. 2 headings driven from opposite shafts toward each other, each working on its own survey chain without any cross-check possible until they were close enough to hear each other blasting through the rock, would meet at a point that either confirmed both chains had held or showed where one had not. Horizontal alignment at the breakthrough had to be within a few inches over runs of 1,000 feet or more. Vertical alignment was held to similar tolerances. The men holding those lines had no laser instruments, no electronic distance measurement, no way to verify themselves against anything except the plumb wire and the marks on the wall. They had a precision transit, a steel wire, and the experience of surveyors who had spent careers learning to hold a bearing in the dark. On City Water Tunnel number 2, the headings connected. The concrete lining was poured continuously through each connection point without significant correction to the tunnel axis. The tunnel opened for service in 1936 and has carried water without interruption since. It has never been shut down for a physical inspection because the city has no spare capacity in the rest of the water tunnel system to absorb its load during a shutdown long enough for real inspection work. No engineer has stood inside the tunnel at its working depth since the water went in. The condition of the lining is assessed through pressure readings and flow measurements taken at the surface, through the continued absence of the kind of failure that would announce itself unmistakably in the data. The structure built by the Sandhogs of the 1930s is assumed to be intact because it has not failed. That assumption will hold until a third tunnel, under construction since 1970, provides enough redundant capacity to allow a shutdown and a direct look at what is inside. That third tunnel uses tunnel boring machines that cut through rock on a mechanized cycle. Laser guidance that holds a line to tolerances the plumb wire surveyors of the 1930s would not have thought achievable, and geological models built from far more complete boring survey data than existed when the second tunnel began. The Sandhogs still go down. The name did not go away when the methods changed. The men who built tunnel number 2 left no account of working 800 feet below a city that depended entirely on their judgment, in rock that the maps did not fully show, with instruments that demanded absolute precision in conditions that worked against it. They left the tunnel running. It still is. Thank you so much for watching until the end. If you loved this story, check out the other videos on your screen now. I think you'll really enjoy them. And don't forget to subscribe if you haven't already. See you in the next story.